The journey of steel begins with the billet, a semi-finished steel product that serves as the primary raw material. They are known for their strength and consistency, providing the perfect starting point for further processing into steel bars, wires, and other shapes. The billets are transported to the processing area using a completely automatic raw material handling system. This system eliminates manual handling and ensures smooth and efficient movement of billets to the next stage. Automated handling minimizes human error, improves safety, and ensures that the billets are correctly positioned for further operations. Once the billets reach the reheating furnace, they are subjected to controlled heating. The furnace brings the billets to a malleable state by heating them to temperatures of 1,100 to 1,300 degrees Celsius. Advanced technology ensures uniform heating and reduces fuel consumption, leading to energy efficiency and lower environmental impact. Uniformly heated billets are essential for ensuring consistent quality in the subsequent rolling process. In the rolling process, the heated billets are passed through a series of rollers to shape them into the desired cross-section, such as rods or bars. The rolling process reduces the thickness of the billet and ensures uniformity in dimensions. Precision-engineered rolling mills apply the right amount of force to achieve consistent results while maintaining the structural integrity of the steel. The rolling mills are supported by hydraulically pre-stressed stands. These stands ensure that the rollers maintain precise alignment and exert consistent pressure during the rolling process. To enhance efficiency and prevent material wastage, the PLC, Programmable Logic Controller, controlled cobble shear is employed. The straight-line mill ensures that the steel rods or bars move in a straight path during the rolling process. Loopers are advanced mechanisms that manage the tension of the steel rods or bars during the rolling process. PLC-controlled loopers adjust the tension automatically, preventing overstretching or slack. This precision control ensures that the material flows smoothly through the rolling mill, maintaining consistency in dimensions and surface quality. After the rolling process, the steel rods or bars are cut to the desired lengths using a PLC-controlled dividing shear. This system ensures superior length control with minimal tolerance for error. The entire manufacturing process is monitored and controlled from the main control desk, equipped with state-of-the-art PLC systems and advanced monitoring tools. Once the steel bars or rods are cut to length, they are transferred to the rake-type cooling bed. This automatic system allows the hot steel to cool evenly in a controlled environment, preventing warping or deformation. After cooling, the steel bars are trimmed further using a PLC-controlled cold shear. This system ensures precision cutting at room temperature, resulting in clean, smooth edges. Accurate trimming enhances the product's visual appeal and ensures it meets dimensional specifications. The trimmed steel bars are then transported to the next stage using an automatic chain transfer system designed by Sundbrista, Sweden. In the final stage, the steel bars are bent and bundled automatically. Advanced machinery ensures that the bars are bent to precise angles and bundled according to customer requirements. This automation speeds up the packaging process and prepares the steel for easy transportation and distribution. The process began with detailed engineering to design the monopile and generate workshop drawings. These drawings served as the blueprint for production, specifying dimensions, materials, and weld positions. The required steel plates were delivered to SEEF, either already beveled at the plate mill or prepared internally. Plate beveling was critical to creating proper weld seams for the assembly process. These plates formed the building blocks of the monopile. During the rolling and tack welding phase, the steel plates were carefully formed into cylindrical shapes using precision rolling machines. This step transformed flat steel plates into cans, which are the foundational segments of the monopile. The rolling process required meticulous control to ensure the correct diameter and curvature. Once shaped, the edges of the cans were secured using tack welding. This temporary welding step held the structure in place, maintaining its form and alignment for subsequent welding and assembly processes. In the longitudinal welding and milling stage, the cans underwent internal longitudinal welding first, where automated welding systems ensured precise and consistent seams along the length of the structure. After the internal welds were completed, the external weld areas were prepared through milling, which smoothed and shaped the edges for optimal weld penetration and adhesion. This was followed by external longitudinal welding, creating robust seams. Once the cans, cones, and other sections were completed, they were transported to SIF's facilities at Maasvlakte 2. This state-of-the-art location was specifically designed to handle the large-scale production of monopiles. At Maasvlakte 2, the individual cans and cones were positioned, tack-welded, and joined using circumferential welding. This included internal circumferential welding, external milling to refine the joint, and external circumferential welding. Precision was critical to ensure structural integrity and alignment. Comprehensive testing followed the welding processes. Ultrasonic testing verified the quality of the welds, while optical control ensured accurate positioning. The monopile's size and shape were remeasured to confirm compliance with specifications. The monopiles were then coated in a specialized hull. This process included washing the internal and external surfaces, blasting, metallization, and applying protective coatings to guard against corrosion and environmental stress. Finally, the finished monopiles were stored and prepared for shipment at Maasvlakte 2. This location facilitated efficient transportation to offshore wind farm sites, completing the production cycle. SMX radial forging machines are equipped with a maximum press force of 18 meganewtons, a tool opening of 800 millimeters, and can handle ingots weighing up to 8 tons. They can produce forged products with a minimum diameter of 130 millimeters and a maximum forging length of 18 meters. These machines are versatile, accommodating various shapes, including round, square, octagonal, flat, and complex forms like step shafts and seamless tubes with minimal wall thicknesses. The machines are particularly suited for applications requiring precise dimensions and high-performance materials, such as railway axles, aerospace components, energy plant parts, and offshore pipes. The forging process is fully automated after the ingot is removed from the furnace. A loading manipulator ensures precise positioning of the ingot for seamless insertion. The machine employs advanced software, such as CumForge, which calculates the pass schedule based on a database of over 400 materials and their flow curves. This ensures that the initial forging passes penetrate deep into the material, achieving a homogeneous microstructure across the entire radius. During forging, manipulators operate under computer control to maintain precise synchronization. The carriage advances at an even pace, while the tong unit stops synchronously with the strokes, ensuring precise handling of the workpiece. This level of coordination allows for continuous workpiece transfer during forging, resulting in exceptional forging accuracy and surface quality. One of the standout features of the SMX radial forging process is its high productivity. The machine can deliver up to 240 smoothing strokes per minute, depending on its size. This high-speed operation significantly reduces the time required for forging while maintaining precision. The near-net shape forging minimizes material waste and reduces the need for extensive post-forging machining, leading to cost savings and shorter production cycles. The hydraulic radial forging process is ideal for producing critical components, such as railway axles, including double axles forged in a single heat, highly stressed parts for energy plants, reliable aerospace components, and offshore pipes capable of withstanding extreme conditions. By achieving near-net shape production directly from the ingot, the process ensures high material yield and energy efficiency, contributing to its economic and ecological benefits. Produces 1 million tons annually of high-grade automotive steel. Blooms size 390 by 530 millimeters, 3.5 to 8 meters long, undergo hot-cold charging with precise weighing. The reheating furnace, with a 200 tons per hour capacity, ensures consistent bloom heating for optimal rolling and metallurgical properties. Removes surface scales from blooms using high-pressure water jets. 47 inches too high reversing mill with 1,200 millimeters rolls and 2,600 millimeters barrel. Bar manipulators equipped with rams and tilting fingers ensure efficient handling and precise positioning of blooms during the rolling process. The rams push the bars into place, while the tilting fingers adjust their orientation, improving workflow and reducing manual intervention. This system enhances safety, accuracy, and operational efficiency within the breakdown mill. Facilitates smooth bar transfer from breakdown mill to next process. Hydraulic shear crops bar ends with a 1,000-ton cutting capacity. (45° turning of intermediate square products before continuous mill. High-pressure water secondary descaler before continuous mill. 6-stand continuous finishing and sizing mill. Finishing stands Redring Series 5 feature 1,030 mm roll centerline, 1,200 mm barrel, and quick stand changes. Sizing stands CGA offer 870 mm roll centerline, 1,200 mm barrel, with quick stand change capability. ProScan laser profile gauge ensures precise measurement of bar dimensions for consistent quality and accuracy. Exit roller table transfers bars, while layer forming ensures proper alignment and stacking for cooling. Removable heat-retaining covers maintain optimal temperature during bar handling, preventing premature cooling and ensuring quality. The cutoff machines feature 2 metallic disc saws with a 1,800 mm nominal diameter, efficiently performing head cropping and dividing bars into commercial lengths. This ensures precision and consistency in final product sizing. The bar end marking station labels each bar for identification, ensuring traceability and quality control. Turnover cooling beds rotate bars during cooling, ensuring uniform temperature distribution and preventing distortion. ProScan laser profile gauge provides real-time, precise bar profile measurements, ensuring dimensional accuracy and quality consistency. The flying dividing shear, with a 300-ton capacity, enables precise continuous cutting of moving bars. The exit roller table ensures smooth bar movement, while layer forming organizes bars for efficient handling. Cutoff machines with 1,800 mm disc diameter perform precise head cropping, and divide bars into accurate commercial lengths efficiently. The bar end marking station applies clear identification marks to each bar, ensuring product traceability, batch tracking, and quality assurance. The bar collecting and bundling system organizes bars into bundles of 2 to 10 tons, ensuring efficient handling, storage, and transport. Bar bundles weigh 2 to 10 tons and measure 4 to 12 meters. The bundle binding station securely ties bundles for safe transport. Run-out roller table moves bars to weighing for precise measurement. The steelmaking journey begins with the mining of taconite, a type of rock containing crude iron ore. This rock is exploded from the earth and ground into powder, allowing the iron ore to be separated using powerful magnets. The extracted iron is then formed into marble-sized pellets, which will later be transformed into molten iron. Simultaneously, bituminous coal is converted into coke, the carbon-rich fuel essential for the steelmaking process. The coal is crushed, sealed in airtight ovens, and baked for 12 to 16 hours. The resulting solid carbon fuel is ready to be combined with iron ore pellets. The next stage occurs in the blast furnace, where iron ore pellets, coke, and limestone, used to remove impurities, are combined. A continuous blast of superheated air ignites the coke, creating intense heat to convert the raw materials into molten iron. Temperatures inside the blast furnace can reach a staggering 2,700 degrees Fahrenheit. In large furnaces, over 90,000 tons of molten iron can be produced daily. The molten iron is tapped from the furnace into giant ladles and transported to the basic oxygen furnace for the next stage, steelmaking. In the basic oxygen furnace, molten iron is mixed with recycled steel scrap. High-purity oxygen is blown into the mixture at supersonic speeds, causing a spectacular display of sparks as the iron transitions into molten steel. This stage is highly efficient, with up to 250 tons of steel being produced in under 45 minutes. Once the molten steel is prepared, it is transferred to a ladle and often undergoes additional refining processes, such as vacuum degassing, which improves its formability. The steel is then poured into a tundish, a funnel that channels the molten material into a continuous caster. These slabs are typically 8 to 9 inches thick and 3 to 5 feet wide. They are cooled to a red-hot solid and cut into sections up to 40 feet long for further processing. The resulting slabs mark the transition from raw materials to semi-finished steel. The semi-finished slabs are reheated to 2,400 degrees Fahrenheit and pass through the hot strip mill, where they are descaled and rolled thinner and longer. This process is completed in finishing stands, which further reduce the thickness of the slabs. The cooling process in steelmaking occurs after hot rolling, where molten steel is formed into slabs or coils. These are cooled to a red-hot solid in a controlled environment. During this stage, precise cooling techniques, including water sprays and air, ensure the steel's structural integrity and prepare it for further processes like cutting, shaping, or finishing. Steelmaking is a process marked by constant innovation. From the precision of automated equipment to the development of new steel grades, the industry continues to evolve, ensuring steel remains a cornerstone of modern life. The production of ammunition, specifically the forging of 155mm artillery shells, is a highly specialized process requiring advanced machinery and precise techniques. At EAS's Hymettus plant, this process is conducted using a state-of-the-art 2,000-ton EUMUCO hot forging press. This impressive piece of equipment ensures the production of durable, high-quality shell casings, capable of withstanding the extreme pressures and temperatures experienced during artillery fire. The process begins with the selection of high-strength steel billets, chosen for their ability to meet the rigorous demands of military specifications. These billets are heated to elevated temperatures in a controlled environment, ensuring the metal becomes malleable without losing its inherent strength. The 2,000-ton EUMUCO press then applies immense pressure to shape the heated billets into the desired shell dimensions. The EUMUCO hot forging press offers several advantages in this process. Its high tonnage capacity allows for precise forming of the 155 mm shells, ensuring consistent wall thickness and structural integrity. This level of precision is critical, as even minor defects could compromise the shell's performance and safety. The automated systems integrated into the press also enhance production efficiency, enabling EAS to produce shells at a scale and quality suitable for both domestic and international defense contracts.